boldly going where no science show has gone before. The Naked Scientists.
Oh, well, hello, and welcome to this week's Naked Scientists. We've got Diana O'Carroll here. Hi, Diana.
Hello.
And also Dave Ansell. Hello, Dave.
Hi, Chris.
And, of course, I'm Chris Smith. Now, coming up this week, how scientists have discovered a new way to make large numbers of stem cells that can be used to treat leukemia. And these are stem cells that have been taken from the umbilical cords of newborn babies. Also, the scientific reasoning behind the needle in a haystack phenomenon, why hunting for rare things actually makes them much harder to find, and we'll find out what the relevance of that is to security at Heathrow. Plus, how women can affect men's testosterone levels. Indeed, it is official. Your partner's menstrual cycle is probably affecting your hormones, and we'll find out what the consequences might be in just a minute. Diana.
Thanks, Chris. And also this week, it's our science question and answer extravaganza. We're attempting to solve all your scientific problems, including, can tapping a tin of fizzy drink stop it from exploding all over you? Can we create artificial nerve signals? And were people less smelly in medieval times?
Thanks, Diana. And in this week's very seasonal kitchen science, I'll be showing you the science behind putting salt on the roads to keep them frost-free and why seawater might not be an ideal alternative. If you want to have a go at this week's experiment, we need some ice, a bowl, some salt and a thermometer.
Thank you, Dave. So, a very cool kitchen science in the offing there. In the meantime, if you have any questions for us, then you can drop your comments or your feedback to us on email. The email address is chris@thenakedscientists.com. You can also Twitter at us, of course. It's @NakedScientists.
The Naked Scientists Podcast. Powered by UK Fast, the UK's best hosting provider. On the web at ukfast.net.
Hello, and welcome to this week's Naked Scientist News Flash with me, Chris Smith.
With me, Diana O'Carroll.
And with me, Dave Ansell.
Now, first up this week, scientists have discovered how they can use a new technique to make very large numbers of stem cells. Now, a big problem with making stem cells outside the body is that when you try and grow them, for instance, in a dish, and using things like growth factors to make them grow, the stem cells lose their stem cell-ness. They lose their ability to turn into lots of other kinds of cells, and they try and become very specialist kinds of cells, and that limits their use. But what scientists this week have announced in the journal Nature Medicine, and this is Colleen Delaney, who's at the Fred Hutchinson Cancer Research Center over in Seattle in America, they have found a way to grow very large numbers of cells called CD34 cells, and these are stem cells that you can collect from the umbilical cords of newborn babies. And these cells can be used to do bone marrow transplants. The problem is that the number of them that you get from a newborn baby is so low, it's only about 10% of the number you would need to treat an adult. So how do we get enough cells? Well, what they've done is to find that if they use a chemical called Notch1, and this is a signalling protein which seems to make stem cells grow in the bone marrow in the body anyway. If you incubate these stem cells with this Notch1 signal, then you can increase their numbers. In fact, they were able to grow 164 times as many cells as you would have normally in the dish doing this. And they demonstrated that these cells do remain as stem cells. They could put them into mice that didn't have an immune system, and they would get a new immune system using this technique. They've also been able to do this in patients who have got leukemias and are undergoing bone marrow transplants for their leukemia. So they took 10 patients who had a very severe leukemia and needed a bone marrow transplant, and in those patients they took umbilical cord blood stem cells, grew them up using this technique, and managed to get those patients to engraft. In other words, you put the stem cells into the patient, they go to the diseased bone marrow, replace the marrow that was there and was diseased before, and give the patient a new bone marrow. And the exciting finding was that in the patients they treated with this technique, then their bone marrow came back to life. In other words, started to make new blood cells 10 days sooner than using traditional techniques. So it looks like you get a much better survival advantage, because the sooner that persons get their cells back, the sooner their immune system starts to work again, and the more likely they are to have a good outcome. So a very encouraging piece of work.
Well, it's a fantastic discovery, and it's even better because it's going to be tailor-made to the patient as well. Well, something else that is perhaps tailor-made to me is that I'm quite scatterbrained at the best of times, especially when it comes to organising my things, and I'll often spend an evening rifling through bits and pieces which, of course, were filed away in a safe place. And it's said that when you're looking for unusual objects, you're not as good at finding them. So if you're security staff at an airport and you have, say, 600 bags to scan, of which 15 contain contains some sort of weapon, you're much less likely to find all 15. Proportionate to the number of things, searchers will make more errors if the object they're looking for is rare. As lead researcher Jeremy Wolf said, if you don't find it often, you often don't find it. And the reverse is true if you're looking for something that occurs more often, such as sun lotion, in which case you might think you can see it when it isn't there. In Current Biology this week, the researchers from Harvard have been looking at why this happens, and they used 2 groups of between 12 and 13 volunteers to search through some computer-generated bag contents. And common sense might tell you that because something's rare, you need to look through more boxes or bags, and your brain just gets used to saying it's not there all the time, and so you start to miss the thing you're looking for. But the new study shows, however, that it's actually the "ooh, it's there" response which happens more slowly with rare objects. And it's an adaptive behaviour, so that in terms of our ancestors, if you were foraging for food, you'd be more likely to stay in areas where it was common and less likely to stay in areas where it was rare. And this could be really useful in training security staff at airports or even for radiologists looking for tumours. And the researchers say that if they spend a couple of minutes doing a simulated search for common weapons or tumours, then they might do a better job of really finding rare ones for the next 30 minutes or so.
Because it re-entrains them.
Exactly, yeah.
How extraordinary to think that we're victims of our evolution, that because we're commonly looking for things that are common, it kind of makes looking for things that are uncommon, which is the very thing we want to do in science and we want to do at airports, as you say, and in radiology, much more difficult.
Yeah, unfortunate, but never mind.
Now, a living cell is an immensely complicated chemical machine working with thousands of interacting molecules. Unfortunately, it doesn't come with an instruction manual. Now, if I'm given a machine which I don't understand, the first thing I do is start prodding it and seeing what happens. And this is what biologists have been doing for the last 100 years at least. And now one of the biological equivalents of prodding a cell is by introducing new molecules into it and then studying the consequences. Unfortunately for biochemists, a cell is bounded by a membrane which is deliberately designed to filter the molecules entering and leaving the cell. If you didn't have it, it wouldn't work at all. You can get around this already by genetically altering the cell to produce a molecule you want, doing lots of very clever chemistry, or even by injecting the molecule directly into an individual cell by hand. These are very laborious processes that only work for certain types of chemicals. Now, Alex Shelek from Harvard University and colleagues has developed a far easier method. They've taken vertical silicon nanowires, essentially a forest of little silicon spikes, a few tens of nanometers across and about 100 nanometers high, and then covered them in the molecule they want to inject into the cells. They then just put the cells on top of them, and the cells then slowly settle down over about an hour and being penetrated by these nanowires. Once this has happened,
a bed of nails for cells, isn't it?
Exactly,
really?
Just like that. But it doesn't seem to hurt them at all. They've grown cells for 5 weeks sitting on these nanowires, and they seem perfectly happy.
And the nanowires do actually go in through the cell membrane and get inside the cell.
Yep, they've found 95% of the cells they put on top of this forest show that they've had the chemicals being put inside them.
So whatever's decorating the nanowires then basically is moved inside the cell and dissolves in the contents of the cell.
That's right. They've injected DNA, RNA, peptides, proteins and small molecules into many types of cells and detected the effects of the molecules inside the cells. They can experiment on hundreds of cells at once, so you get good statistical data in the results. And even better, the team have been able to inkjet print hundreds of small patches of different chemicals and different combinations of chemicals at different concentrations onto a slide. They can then put lots of cells over the top, and you can do hundreds of experiments all at once. And they've even managed to take the cells off again, off the spikes, and they seem perfectly happy. So it opens up the possibility of doing more than one experiment on the same cell, one after another.
Because obviously scientists have had the ability for a while to use genetic techniques to turn on various genes in cells and make chemical markers and things, but something like this that means you could put other chemicals into cells, maybe toxins or things, and do it in a very standardised way that means you can measure the same cells many, many times over to work out reproducibly what's going on. That could be really powerful, I can see.
And you can even control the dose. Yeah, I don't know whether it would be used in any therapies anytime soon, but certainly as a way of learning about cells, I think it could be very important.
Indeed, a very powerful tool. Thank you, Dave. Now, very interesting this week. I've always been questioning this because listeners to The Naked Scientist for a little while might remember me covering a story back in about 2008. A guy called Geoffrey Miller showed that if you look at lap dancers in Albuquerque, imagine having a grant to go to a lap dancing club. He was asking these lap dancers in these clubs to record how many tips they got at different times of the month. And they found that women who weren't on the contraceptive pills, so they had a normal menstrual cycle, in the middle of their menstrual cycle, around day 14, which is when you're most fertile. You're most likely to get pregnant if you have sex then. At that time, their earnings went up by 200% compared with women that were on the pill or at other times of the month. So that showed that it wasn't something to do with beauty, it was something to do specifically with signals coming from the women and influencing the men who are giving them tips in the lap dancing club. Now, no one could understand whether it was because the women were feeling more, attractive around day 14. Perhaps they were making themselves look nicer, or they were sounding warmer, nicer, because women's voices change menstrually as well. Maybe that was what was inducing the men to be more generous. No one knew. But now there's a study out this week which caught my eye. It's from a couple of guys at the Florida State University, Saul Miller and John Maynor, and they've written this in the journal Psychological Science. What they did was to recruit 37 male students. They're aged 18 to 23, so these are rumbustious young men, and they got 4 females who were not on the pill, so they had normal menstrual cycle, and they asked these ladies around the middle of their cycle, when they're most fertile, to wear a T-shirt every night for 3 nights. So day 13, day 14 and day 15 of the menstrual cycle, they wore these T-shirts. They then gave them back to the researchers, who put them in an airtight bag and kept them. Then, later on in the month, at day 20, 21 and 22, the women repeated the experiment. So what they've got now are T-shirts worn by these women at times of the month when they're very fertile and times of the month when they're not going to get pregnant if they were to have sex at that time. They then took these bags to these guys who they'd recruited and asked them to sniff them. But they also included some control T-shirts to make sure it was a fair test, and they took saliva samples from them before they sniffed anything and after they sniffed things, because you can measure testosterone levels from saliva. And what they found was that when the people sniffed the T-shirts that had been worn by the girls when they were in the middle of their menstrual cycle and much more likely therefore to get pregnant if they had sex, what they found was that those individuals were rated as much smelling much more pleasant when they smelt the T-shirts. The men said that smelt nice, and their testosterone level was higher, much higher, significantly higher, compared with individuals sniffing shirts from controls, in other words, shirts that haven't been worn by anybody, or shirts worn by girls later in the month. So this suggests that some kind of signal, which is oozing out of women's bodies and changes with their menstrual cycle, is influencing the way that men's brains respond to women, and it's doing that by producing more or less testosterone, which in itself is our arousal hormone, or one of them, and therefore makes you feel fruitier, for want of a better term. So women are manipulating the way that men feel. I think that's wonderful. We've known that women do that to other women for a very long time. Women, if they live together, synchronise their menstrual cycles. No one's yet shown, and this is the first demonstration, that women may actually change the way that men behave towards women and perhaps even towards other men, because testosterone makes men quite aggressive too.
So do you think this could be the start of smelly T-shirt competitions or something?
Well, no comment. I obviously don't know your washing techniques, but I think it's an intriguing observation, and it's been a sort of gap in our knowledge that's been needing to be filled for a little while, actually.
So do they think that it's a chemical released in the sweat rather than perhaps different species of bacteria that might respond to different temperatures?
No one knows. We only know that it's a smell because this experiment isolated the women from the very thing that was influencing the men. In the lap dancing club, the question was, well, the men could see the women, so was there something else going on? Was it the women influencing the men? Here, it's just a smell. So we don't know what's making the smell change, but there's clearly something which is going into the men's noses and making them change their behaviour.
Fascinating.
Chemically as well as in other terms.
All right, well, moving on to a less smelly gas. We've heard about sequestration deep beneath the earth with CO2, and now here's another way of dealing with the CO2 problem, and it's copper. It's quite tricky to extract CO2 from air, as it's quite a stable molecule, at least compared to the other component of air, which is oxygen, and also nitrogen as well. And so most of the time, gaseous oxygen will bond to a metal, for example, before carbon dioxide does. But this new copper complex, reported in the journal Science this week, can ignore boring old O2 and go straight for CO2. And the researchers, led by Elizabeth Baumann at the Leiden Institute for Chemistry, say that typically the problem with oxygen is that it will gain an electron more readily than CO2. But this copper complex will happily donate electrons to carbon dioxide instead. So to extract CO2 from the air, they put this copper complex into solution, and the researchers say that the atmospheric CO2 to which it's exposed will be absorbed. And then to extract the carbon again, they just added a lithium salt solution, easy as that. They put a low voltage across it of about 0.03 volts, and presto, the organic compound precipitated out. And as a bonus, the byproducts can be converted into useful compounds, which can be used in things like cleaning products and wood preservation products. What's really useful is the copper complex can be cleaned at the end of the reaction and reused as a catalyst. So they managed to do this 6 times in 7 hours. And compared to other methods of sequestration, it's actually really cheap. And there's a possibility that accessible copper ores might run dry not too far in the distant future. So I don't know how long that might last.
Presumably it's energetically favourable as well. Have they done the sums to prove that it is actually worth doing it this way?
Well, yeah, because the voltage that they put across it to clean it, again, is so very low compared to other methods that, it's really cheap in terms of energy.
Thank you very much, Diana. Right, well, you couldn't really have escaped the coverage this week of the disaster that's happened in Haiti. We've heard lots and lots of reports from Port-au-Prince, which is the capital city in Haiti, where they had the earthquake earlier this week. It was said to be magnitude 7 on the Richter scale, and the number of people who may be dead or injured runs into many thousands. Loads of those reports have looked at the humanitarian crisis, but very few of them have actually looked at what's going on geologically. So we've invited Dr. Paul Mann, who is a geologist at the Institute for Geophysics at the University of Texas at Austin, to join us and fill us in a bit more. Paul, welcome to The Naked Scientist.
Okay, thank you for having me.
It's a pleasure. Could you first of all, in practical terms, explain to us what a magnitude 7 quake is?
Okay, the term magnitude refers to the Richter scale, which is a way to assign a number to quantify the amount of seismic energy released by an earthquake. It's a logarithmic scale, so an earthquake with a magnitude 5 on the Richter scale would be 10 times larger than a magnitude 4. So just to tell you what the effects of these different magnitudes might be as a person, the 0 to 2 level is not felt. The magnitude 3 level would be felt, but there's no damage. Okay, magnitude 4, you have shaking with limited damage. Magnitude 5, you're talking major damage. Magnitude 6 is considered a strong earthquake, and that can cause destruction, especially in populated areas. Just to give you an idea of how many magnitude 6 earthquakes there are per year, there's about 120. Magnitude 7, which is the size of the Haiti earthquake, is considered a major earthquake with damage over large areas. There's about 18 magnitude 7 events per year. Remember that most of them are occurring in unpopulated areas, so the Haiti event is unique in that respect, in that it occurred in a very densely populated area, therefore you have a lot of casualties.
And geologically, Paul, what actually went on to cause this to occur?
Okay, faults, basically we're on a plate boundary. We're on the boundary between a small plate, it's called the Caribbean plate, and the North American plate. And if you can sort of visualize this geographic region, this is the Caribbean. We've got Haiti and Dominican Republic sharing the island of Hispaniola. We've got Jamaica off to the west. We have Central America farther to the west. So through this area runs a roughly east-west trending fault system. We call it a strike-slip fault. And what that means is the two sides of the fault are moving horizontally with respect to each other. But this fault movement doesn't occur in a steadily slipping way. Instead, it occurs with these sort of spasmodic jerking motions. These faults, because they're so irregular along their surface, can actually store motion for hundreds of years. So what's happened in Haiti is the fault is basically a frozen surface. It hasn't moved since, we think, about 1770. As the plates keep moving past the fault, which is frozen, the fault reaches a point where it can no longer sustain the stresses that have built up along it. So what we think happened in Haiti was that suddenly the fault ruptured in order to catch up to the plates, which have been smoothly moving past it for these hundreds of years.
And when you say energy is being stored in the fault, in what form is the energy being stored? Because obviously the plates are trying to move past each other a couple of centimetres a year. The fault isn't going anywhere. So where is the energy actually going, and how is it being stored there?
Well, the energy is elastic energy, and it's being stored in the rock beneath the fault trace that we see at the surface. And remember, the surface area of this fault is very large because it's cutting down through the upper part of the crust. This particular earthquake, its hypocenter, or the zone of rupture at depth, was about 5 kilometers below the Earth's surface. So it gives you an idea of the large surface area along these very irregular fault planes. But it would be analogous to drawing a rubber band back, and that rubber band is storing elastic energy to the point where the rubber band breaks, and that would be analogous to the earthquake.
You made some predictions a couple of years ago, a year and a half ago, that this may be about to happen. How did you manage to do that?
Well, in seismology, we avoid use of the term prediction, and to predict something, you have to be able to precisely state many aspects of the earthquake, including the epicentral area, or where the earthquake occurs, the size of the earthquake, such as magnitude 7 in this case, and most importantly, when exactly that earthquake is going to occur. For example, it's going to occur 2 weeks from now or 2 years from now. Unfortunately, in seismology, there is no success by anyone in predicting earthquakes. What we did with this event is what we call forecasting, much like a meteorologist might do on a weather forecast. We stated that we had a major fault, which we call the Enriquillo Plantain Garden Fault Zone. We know this fault extends about 600 kilometers between Jamaica and southern Haiti. We know that from our GPS studies, which were done by Dr. Eric Calais at Purdue University, that this fault was moving at a rate of about 7 millimeters a year. And remember, the fault itself isn't moving, but the plates on either side of it are moving at that rate. And finally, from our historical records of Haiti, we know that the last fault that moved, or the last large earthquake, which we think was related to this fault, occurred in the 18th century. So we take the amount of time, roughly 250 years. We take the rate derived from the GPS study, 7 millimeters a year. We calculate how much strain has accumulated, which was about 2 meters. We can convert the amount of strain accumulated to the size of the expected earthquake, which we had said was about 7.2, and the event turned out to be 7.0. But I think the key element here is that we did not make any statement about this earthquake was going to occur on January 12th. All we said was that this was an area of high seismic risk, especially given the existence of Port-au-Prince, a city of 2 million people, very poor construction practices, and it's only 20 kilometers north of the fault.
And just to finish off very briefly, Paul, what's the chances that this is going to happen again very, very soon? As in, do you think this is done for now, or do you think that there's a lot more energy still sitting there and we should expect this to rumble on a bit longer?
Well, one of the interesting aspects of these type of strikes of earthquakes is that the release of strain over an area, in this case of about 80 kilometers, can actually cause an increase in strain on the adjacent segments of the unruptured fault. And there are many people now at the U.S. Geologic Survey and other universities who are working on models which are trying to predict or to forecast whether these adjacent segments of the fault will rupture and what the time frame might be. But again, with any studies of earthquakes, we have to be very careful about using this word prediction just because it is a very inexact science at this point.
Okay, thank you very much, Paul. We'll leave it there. That's Dr. Paul Mann, who is from the University of Texas at Austin, telling us about the geology underlying the terrible event that we've seen happening in Haiti earlier this week.
Keeping you abreast of the world's best science, The Naked Scientists.
You're listening to The Naked Scientists with Chris Smith, Dave Ansell and Diana O'Carroll. This week we're answering your questions. If you'd like to contact us through Twitter, it's @Naked Scientists, or you can send an email to chris@thenakedscientists.com.
Got a couple of things coming in already. Setep, or maybe it's Set EP on Twitter, says, how many days in the month can a woman become pregnant? Well, the fertile window is around the time of ovulation, which is day 14. So you're really looking at 2 or 3 days either side of that, because sperm can persist survive inside a woman for 2, maybe 3 days. And so that's why it's really important to use safe sex practices ahead of ovulation, and also the time of ovulation can vary by a couple of days in some women. So it's really important to avoid, if you don't want to get pregnant, unsafe sex in that week in particular. We also heard from Viswald Titanium, who's in Second Life. Hello to everyone listening to Second Life. He says, I wonder if the women attracting men with the testosterone story is intentional. The women, for instance, wear additional perfume, perhaps subconsciously during those periods. Well, that was what people said about the study done on the lap dancers, that perhaps the women were making themselves more attractive to the men, and it was a female behavioural thing that was making them more attractive. What the researchers sought to do with this new study was to iron that out by making sure that the women who wore the T-shirts overnight that the men got to sniff only bathed using a neutral-smelling soap. They all used the same cosmetics. They didn't wear perfumes and other kinds of things. They avoided eating foods that might make them stink, like garlic. They actually say that in the paper, so I think it's true. And so they attempted to control for that. So we think it's actually some other chemical which is in some way stimulating them, the men. But we don't actually know what it is yet. That will come next, I guess. Now, Dave, really good question, which is highly seasonal given this cold weather. Martin Taylor has said, why are my windows so drafty? My understanding of the second law of thermodynamics, and perhaps you can explain what he means by that, is that heat moves from a hot body to a cold one. So can you explain to me why cold air is flowing into my very nice warm room through a gap in a badly fitted window? I've proved that cold air is moving in this direction by placing some soft tissue paper in the gap.
Yeah, you're entirely correct about thermodynamics. If you've got two stationary objects and you join them together thermally, heat will always flow from the hotter object to the colder object. It's actually pretty much how we define temperature. So what's happening with your windows, because definitely cold air is coming into your house. That's because the situation is a bit different. You're not putting two objects together and cold, as it were, is moving into your hot house. What's actually happening is that cold air is moving into your house. The laws of thermodynamics say nothing about where air goes, and they don't disallow this. So basically, large lumps of objects can move around as they like, not ignoring the laws of thermodynamics, but they don't constrain them in that way. But definitely, heat will move from a hot object to a cold object otherwise.
Thank you very much, Dave. Now, I've got a question, probably this one's for you, Diana. It's Sarah, possibly Sarah. She says, Chris, when comparing medieval times to present day, the lack of hygiene back then seems pretty offensive. Were people then just not as smelly as we are today? In other words, does the processing, additives, antibiotics and hormones in the food that we have today, for instance, affect our body odour? And she's an American who's actually listening to us in Germany.
I think for the most part the answer is probably no. I don't know if you're ever a fan of Blackadder or anything. The stereotype of Baldric, the smelly peasant, is probably quite true. And actually, if you've ever been to any of those reconstruction sites like Jorvik, although that's about 200 or 300 years before the medieval.
It's very whiffy in there.
And exactly. I mean, it's not quite medieval, but I think it gives you a really good idea of what things might have smelled like. And they include all sorts of toilet smells and cooking smells and mouldy thing smells. It's pretty awful. And from what we know from the archaeology, there wasn't a lot of bathing going on for the peasants, at least. And there was certainly in the houses of medieval people, there are all sorts of bits of evidence for maggots and flies and things just living in the house with them. But it may have been for the more upper-class medieval people, like lords and things, they did actually bathe maybe once a week.
They used to keep their clothing near the loo in their castle, didn't they? Because castles had guard robes, which are the bogs, and correct me if I'm wrong, but wasn't that done under the intention that the things that rot your clothes, the moths and things that would make your clothes go horrible, would avoid the stink for the same reason we would?
Yeah, and they were probably slightly better ventilated than the rest of the place as well, because of course their toilets were just,
Indeed,
holes
because your
into
clothes
the
would
abyss.
smell otherwise, wouldn't they? Indeed.
Exactly. So yes, they probably did smell pretty awful. Also, actually, there's another thing I'd like to add, is that if you're constantly being exposed to horrible smells, you're going to be desensitised to them, aren't you? So perhaps, in that sense...
I think there are limits.
Yeah.
I definitely when I've been hiking for a weekend or a week and you just can't wash, but after a few days you don't notice it and everyone stinks and you don't mind, but as soon as you wash then you really notice the effect.
It's all a relative thing. Diana, very good standard of hygiene, we have to say.
Thank you.
Dave.
I've got a question here for you, Chris, from Liam. His question is, does too much calcium make your bones brittle?
Oh, that's actually a very good question. And the answer is yes, it does, surprisingly. Of course, calcium forms up with phosphates to make the chemical apatite, one of the hardest chemicals we know, which is what makes bones hard and stony and tough. But if you have too much calcium, that can be as bad as having too little, the condition osteoporosis, where the bones actually begin to lose their calcification and the matrix of the bone and get weak and are more likely to break. There's another disease called osteomalacia, where you have too little just of the calcium, and that also makes bones weak. But if people actually lay down too much calcium in bone, and there's a condition called osteopetrosis, from petrous as in stony. This is where people can have, say, 5 times the amount of calcium in their bones as they should have. It's a genetic condition. It's very rare. It's familial, and it's I think it also goes by the name Schomburg-Albers disease or something like that, but it's very rare. And in these individuals, they cannot break down. Their cells that break down bone, called osteoclasts, don't work properly, because the way bone is normally formed is that you have an equilibrium between laying down bone and breaking down bone, and that's how bone continuously gets modelled. And if you shift that equilibrium in one direction or the other, you either lose or gain bone. And what scientists have found is that people who have this osteopetrosis, the osteoclasts that normally break down bone cannot work properly. They have a deficiency of an enzyme called carbonic anhydrase, and you need that to break down the calcium phosphate, the apatite, in order to remodel the bone. And as a result, they just keep on making their bones get harder and harder and harder. And as a result, they in fact go beyond the point of being beneficial and in fact become less flexible and more likely to break. So they get brittle.
Yeah, because I did a kitchen science a while ago about because bone's made up of both apatite and proteins, and it's a mixture of the two things. The proteins make it tough and stop it breaking, and the apatite makes it strong. And if you haven't got enough protein in there, it becomes very brittle and it just falls apart.
Thank you, Dave. This is The Naked Scientist with Chris Smith, Diana O'Carroll and Dave Ansell. It's our science phone-in extravaganza. If you have any science questions for us, then do send them in and we'll try and solve them for you. You can Twitter at us. It's at Naked Scientist, or you can send us an email, chris@thenakedscientist.com.
Lifting the lab coat on the world's best science. The Naked Scientists.
And now it's time to join Mira Senthillingham for an update from the world of technology. And this month she's using her artificial intelligence to solve mysteries.
Yes, so it's time for our first technology update of 2010. And I'm here with our resident techie, Chris Vallant. Hello, Chris, and Happy New Year.
Happy New Year to you too, Mira.
So what's been happening in the world of technology over Christmas? I hear that artificial intelligence has been playing a big part.
Well, you said 2010, so I'm going to take you to 221B Baker Street, Sherlock Holmes. Over Christmas we had the release of the new Guy Ritchie film. As part of a trailer for that, if you like, a digital interactive trailer, there's an online game, 221B. Now, what's interesting about that is the way in which it uses artificial intelligence. As part of the game, you get to play as Holmes or Watson. You have to interrogate suspects. You have to ask them questions, and the answers they give help you complete the game. The problem is, when you're asking a game character something, you could ask them it in any number of ways. Just using ordinary English, the possibilities are endless. So your sort of options are, let's do it like one of those old, choose-your-own-adventure game books, essentially. If you want to do A, click here. If you want to do B, click here. That's a bit limiting. So what the game designers decided to do was approach an expert in artificial intelligence to help them enable natural language type interactions with the game characters.
So how does this actually work, and what's different about it?
This is one of the big challenges in game design, natural linguistic interaction with non-player characters. What this does is it uses the chatbot technology to recognise what a question means. Now, it doesn't have any understanding of the meaning of words. It doesn't have lots and long lists of complicated grammatical rules. What it does is fuzzily pattern matches your question. So it's very good at matching your question with the questions it knows how to answer, and does that and produces an answer according to a script. So the real key here is its ability to recognise questions and know what the appropriate answer is. In effect, it's creating a digital actor in the game with a script, but one who can understand kind of what you're saying and respond appropriately.
And now you actually met up with the creator of this to find out a bit more.
Yes, I spoke to Rollo Carpenter, who developed the artificial intelligence running the game characters, and he explained how his system worked.
My work has been all about creating artificial intelligence that talks, that communicates about anything and everything, and that attempts to look intelligent, to appear to be self-aware. The same fuzzy technology, fuzzy interpretation of inputs is used in the game. So it is our role to predict what you, as Holmes or Watson, what you might know at that point in the game, and the conclusions you might draw, the questions you might ask.
But given the nature of language, there are a near infinite number of possible questions you might ask, some grammatical, some not grammatical. So how does the computer understand a question?
It understands by predicting what you will say and finding the nearest match amongst its trillions of predictions.
So essentially, it's kind of pattern recognition. Essentially,
exactly. It is a kind of pattern recognition, but where the patterns are all treated fuzzily. If you mistype a few letters, it's not going to be upset.
You've used the technology you've developed to build artificial personalities, but there is clearly commercial applications for this kind of technology. What do you see as its potential uses?
A machine that can genuinely understand what people say is valuable in almost any number of ways, but some of the most obvious and immediate concern with customer services, support, marketing, and so forth.
So when I ring up a call centre, at some point in the future, I might get a computer?
Indeed. The people at the end of the phone all too often have to work to a very restricted script, and a computer would be capable of handling scripts 10,000 times larger. And so it may actually do its job enormously better.
That was Rollo Carpenter, whose chatbot technology drives the characters in the game.
So, Chris, have you actually had a go on this? And if so, were you able to solve a mystery?
Well, I didn't get as far as solving a mystery. I did try out interrogating one of the characters, and you can see the results of that up on a video on BBC News Online. It does work surprisingly well, actually, asking questions in natural ways, even trying to catch it out a little bit. You can still have a go at the game. It's still up online as we speak. 221b.sh is the web address.
So I'm going to probably have a go on that as soon as possible. But is this also now something we're going to see enter more areas of gaming?
I think it's hard with the big budget games. Game designers have told me the challenge there is essentially that you have very complicated pieces of animation when you have these, for console games, when you have these stunning visuals. You get voice actors to do the dialogue. So spontaneously creating dialogue and the action to go alongside it is quite a big technical challenge, just from the sound and visual side, let alone making that dialogue meaningful. So this is still an area where there's a lot of development to be done. It's still a big technical challenge.
Elementary, my dear Mira. Sounds fun though, doesn't it, that game? I might have a go myself. That was Mira Senthillingham talking to Chris Vallance, who's our resident tech expert, and he was explaining how artificial intelligence in the world of gaming and possibly call centres could be the way forward. Oh dear. Diana.
Right, I understand we have a question from Amanda.
Hello, hi. Yeah, I'm actually having a little bit of an argument with my husband at the moment regarding our electricity bill. It's almost doubled in the last year, and he seems to think that it's because I leave the lights on constantly. I disagree. I think that it's possibly the fact that he plays his Xbox maybe 24 hours a day over the weekend. He's also got a hot tub out in the garden that's heated constantly, a pond which has got a pump on it. And I would just like to know the actual difference between the costs of these various things.
Oh dear, right. I don't want to be responsible for splitting up a marriage.
I know a good lawyer, Amanda. Just thought I'd drop that in.
Okay, well, I'm actually a bit of a games consoler person myself. So this was quite enlightening for me, actually. I've got some numbers for you. So what I've done is I've made the assumption that you pay maybe 15 pence per kilowatt hour, and I guess sort of the euro is on parity with the pound at the moment. So, so let's imagine that your husband is playing playing on a 42-inch LCD TV. That's pretty big, and that will draw about 200 watts. And so so that will probably cost about 3 pence per hour. And if you're doing 2 times 5-hour sessions over the weekend, that's going to be about 30 pence. Now, the Xbox on its own, that draws about 160 watts, so that's going to be 24 pence for the same amount of time for each 5-hour session, so the total will be about 54p. So that's going to be 84p for a 10-hour weekend session.
Sounds like good value.
It's not bad, actually. It's a lot less than I thought it was, which, I was playing on it earlier today anyway.
I thought it was going to be more.
But the hot tub and the pool pump and everything, like the pond pump, that's going to be quite hungry, isn't it?
Now, the hot tub is where it gets a bit serious, I'm afraid. From my research, most hot tubs seem to use about 2,000 watts, which is a lot. And that's going to cost about 30 pence per hour, so that's going to be 90 pence for a 3-hour session, or it's going to be £2.40 for a full day,
so,
and
Amanda,
for a full week.
It's
£16.80.
It's curtains for the fish, Amanda.
Yeah.
You have to eat them. I'd catch them and eat them.
And then, if you want to compare it with your bulb usage, so if you've got energy-saving bulbs, I'm guessing that you're good boys and girls over there.
Some are, but we've got a lot of spots in our house.
Okay.
They, I think, use quite a lot of electric, don't they?
Okay, well, I mean, if you're using a nice 20-watt energy-saving bulb and you've got 3 of them on for 8 hours overnight, 7 days a week, that's going to cost you about 50p. But if you've got the old-fashioned style ones, that's going to be £2.52. But, I'm afraid the whirlpool there or the hot tub, that's going to be the real killer.
Heating all that water up is going to be really costly, isn't it? Amanda, thank you very much. I hope that you can resolve it. I think the bottom line is that no one really is any worse than the other. But the heating up a lot of water in a hot tub is going to be quite costly, but then so are those light bulbs. Maybe consider some energy-saving ones.
That's it. I think you're probably right.
And the 1 megawatt tableau of Christmas decorations you put on the outside of the house this Christmas, that's got to go too, OK?
OK, so we'll be eating fish next summer.
Good to have you on The Naked Scientist. Thanks for calling.
Thanks a lot. OK.
Amanda Berta calling us with her electricity conundrum. OK, I think this is probably one for you, Dave. Greg has been in touch.
Yeah, g'day. I'm Greg from Australia. Got a question about the Large Hadron Collider I was hoping you could answer. I'm curious about the temperatures that they're running the experiments at. Just wanted to know if you could explain why the temperatures are so low. I think it's around minus 270 degrees, and also how they get the temperature that low and how they maintain it.
OK, there are temperatures in the LHC of about 1.9 Kelvin. That's 1.9 degrees above absolute zero, so about minus 271 and a bit degrees centigrade. There's a couple of main reasons for doing this. One of the big ones is the LHC has huge magnets in it, which are used to bend the particles around corners. They have to be incredibly strong magnets. And you can't do that with a normal permanent magnet. You just can't get them strong enough. You have to use an electromagnet. If you made the electromagnet out of normal copper wire, it would just melt in no time in order to get that strong a field. So what they have to use is superconducting magnets. A superconductor is a material which, when you cool it down enough, its resistivity goes to zero, so it will pass a current with no resistance at all. This is great for a magnet because you just start a current flowing and it keeps on going forever. The problem with superconductors is the bigger magnetic field you apply to them, the lower the temperature they start working. So if you want to make incredibly strong magnets, you have to use very, very low temperatures. They're using about 1.9 degrees above absolute zero. And this is actually below the temperature of liquid helium at normal atmospheric pressure. So what they have to do is they take liquid helium, which you've made essentially with a very, very big fridge by compressing gases and letting them expand. And as they expand, they get colder. You then take liquid helium and pump on it, so you reduce the pressure above it, so then it boils and boils and boils until it gets colder and colder and colder down to about 1.9 Kelvin, in fact 1.8 Kelvin, and then they pump that round the system and cool down the magnets.
I would come off that by saying cool, but that would seem like an awful pun. But the bill for doing that must be absolutely huge to do that. Or once you've got it to that liquid state, is it so well insulated that it just stays that way? How does it work?
It is going to need a huge amount of energy because although they're not moving that much energy out of the system, they're probably moving a couple of 100 kilowatts of energy, which by the standards of huge industrial processes isn't very much. The problem is the colder you take the energy from, the harder work it gets. So if you move energy from somewhere room temperature to somewhere a bit hot, a couple of degrees hotter, then that uses very little electrical energy. If you move it from something at 1.2 Kelvin to room temperature, that requires an immense amount of energy.
And the magnetic field that will be generated at those low temperatures of that superconducting magnet, will you get a magnetic field once you've basically fired up the magnet that will just sustain itself because there's no resistance? And will you only be losing the magnetic field because the particles will sap energy from it, so it will therefore need to be topped up for that reason?
The superconducting magnets, once they start going, they essentially work like a permanent magnet. People have done experiments with superconducting magnets, and as far as they know, definitely some of them will keep on going for billions of years. The real problem is if part of the superconductor warms up, at which point you've got a huge amount of electrical energy running around it, all of which is dumped into a very small area of the superconductor, which gets very, very hot. All this liquid helium, which you've got inside there, suddenly boils, and that produces a huge amount of gas, which expands very, very rapidly. And actually, this was a problem they had last year when it all went horribly wrong. This huge amount of gas then pushed the magnets round, billions of pounds worth of stuff got just shuffled round this system, and it caused an immense amount of damage.
Let's hope there's not a repeat. Thank you, Dave. We've also heard on Twitter, @NakedScientist, from Outstan Jing, who says, how do mosquitoes lay their eggs? We never see them. Well, of course, mosquitoes depend on water for their life cycle. Different mosquitoes live in different environments, and as a result, they depend on different types of water, stagnant water, big ponds of water, dumped car tyres with bits of water, that kind of thing. And you can normally tell which species of mosquito you're dealing with depending upon where they're laying eggs. But the bottom line is the mosquito goes down to the water once it's mated, and different species of mosquito lay different eggs in different ways, but they all lay their eggs into water. The certain species lay them as individual eggs which drift off. Some of them lay big rafts of eggs, and the eggs then mature and hatch into little larvae, which then have an aquatic phase. They grow in the water, they eat algae and things, and turn into mosquito larvae that are big. These eventually then mature into full-blown mosquito flies that then take off and come and eat you. And so you just have to keep an eye on a patch of water and you'll see the mosquitoes coming down to lay their eggs.
OK, Chris, I've got a question here from Hamza, and he asks, can we create artificial nerve signals?
Yes, we can. We actually know quite a lot about how nerve information travels. If you can imagine a nerve cell as a bit like a long straw with sides and a container in the middle, a space in the middle, what nerves do is to move positively charged ions, in this case sodium ions, from the inside of their channel, inside the nerve, to the outside world. So the inside of the nerve is a bit minus compared to the surroundings. And when a nerve impulse travels along a nerve, what happens is that some sodium, goes back inside the nerve through tiny pores which are on the surface of the nerve, and this does what's called depolarising the nerve, and it makes that little section of the nerve become transiently a bit positive. Now what that does is two things. One, it starts an electrical signal rather like a Newton's cradle running inside the nerve, but it also activates other little channels and pores on the surface of the nerve a bit further downstream, and they open and let some more plus in to sustain and maintain the propagation of the signal, which in a big nerve is actually travelling along at something like 100 metres a second. It only actually ends up going in one direction, though, because in the opposite direction, behind where it's just been, the nerve then pumps the plus back out again and puts some bit less plus in, so it goes back to being minus. So the nerve resets itself. And this process happens in milliseconds. So you can literally conduct hundreds, if not thousands, of these impulses down a nerve in less than a second. So the information can travel very, very fast. And you can make that happen by stimulating the nerve. If you just apply a little bit of electricity to the wall of the nerve, to the nerve fibre itself, you can actually make that process trigger off, and then it self-sustains. The signal will then propagate along the nerve to wherever it goes, in both directions actually. And scientists use this for a number of reasons. One is that you can artificially activate muscles that way. So if you've been paralysed, for example, you can use techniques like this to restore movement to certain muscle groups by electrically stimulating the nerves that supply those muscles. And another reason is to use brain stimulation. One disease is Parkinson's disease, where this has been done quite effectively. Scientists implant a little electrode in the part of the brain which is involved in the same circuit as is affected by Parkinson's disease and which makes movement. And if you stimulate those bits of the brain electrically, you can trigger off impulses in the right way and at the right rate to help people who have Parkinson's symptoms to overcome those symptoms and move a bit more easily. So it is possible to recreate nerve signals. At the moment, it's fairly low resolution. You're not stimulating individual nerve cells, you're stimulating clusters of nerve cells, but at the same time, you can do that. And also, if you listened to last week's programme, you'll know that we talked about cochlear implants, which are things that can basically stimulate the nerve that conveys hearing information into the brainstem. Well, they're doing effectively the same thing. They're stimulating nerve cells directly to send sound information into the brain.
Yeah, because I remember about a year ago we had a story on Breaking Science, didn't we, with the researcher Andrew Schwartz, who basically monitored the signals being sent from chimps' brains and then translated them using a computer into muscle movements.
Yeah, I guess that's sort of going the other way, isn't it? Rather than putting input into a cluster of nerve cells, what he was doing was recording the activity, understanding how nerves are encoding information and using that, once it's been decoded by a computer, to then drive muscle movements again in an arm. I think they were making the chimpanzees reach out and grab things, weren't they, just by the power of thought? Yeah. Indeed. Right, this is The Naked Scientists, and we're solving your science conundrums. We can be contacted on Twitter at Naked Scientists, or you can send us an email, chris@thenakedscientist.com.
Bringing the facts to bear. The Naked Scientists.
And now it's time for Kitchen Science, and this week we thought we'd get experimental to answer this seasonal question.
Hi, it's Chris Ogilvie here from Wakefield, West Yorkshire. We currently spread rock salt on the roads in the winter weather. The grit's not used to increase traction on the snow, it's just a convenient delivery method for salt, as a salt and water solution remains liquid below 0 centigrade. So if all we need to melt ice and snow is a liquid salt solution, why not just pour seawater onto the roads and pavements? The only salt mines in the UK are in Northern Ireland, Cheshire and Cleveland, but nowhere more than 70 miles from the sea. So using seawater must be cheaper and more practical solution than rock salt.
So Dave, why don't we use seawater?
Well, there's a couple of reasons. The first one is just logistical. Although Chris was thinking that it would be a lot cheaper to get the seawater to the roads because it's much less far to go, seawater is essentially fresh water mixed with about 35 grams per litre of salt. So about a 30th of the seawater is salt. So if you want to get the same amount of salt onto your road, you're going to have to use 30 times as much stuff, which means you're going to have to carry it 30 times as much weight. It's going to be a lot
heavier.
It's going to be a lot heavier, so I'm not convinced about the logistics argument. And the other one is just how well it works as a de-icer. Now, a really important question for that is how cold something will work as a de-icer. So, for example, the traditional thing that you use is salt. So I've just got a set of normal table salt here, and I have got a bowl full of ice cubes. Put a couple more ice cubes in there. Right, so first thing we can do is just try using conventional salt and see what happens.
And so we've got a bowl full of ice there, so Dave is just about to add some salt.
And I've also got a thermometer to measure the temperature as this happens.
OK, so this is representing the grit on the road, essentially.
Yeah, so this is essentially you've got ice on the road, and we're going to throw some salt on it and see what happens.
OK.
So if we start off, the ice is at about 0 degrees C, give or take.
OK, sounds about right for frozen water.
If we throw some salt on the top...
That looks like a lovely cocktail.
You can sometimes hear it's just crackling a bit.
Yeah, just slightly.
OK, now the reason for that might become clear when we measure the temperature.
OK.
So if we measure the temperature of this, it's now down to about minus 10, minus 11 degrees centigrade.
That's quite cold.
That's really quite chilly. And if you look carefully at the ice, you can see it melting where the salt is, and so it's melting away. So what's happening is the salt's causing the ice to melt. And in order to melt ice, you need a huge amount of energy. That's because you're ripping apart bonds between water molecules. And that energy's got to come from somewhere, and the place it comes from is the thermal energy of the surroundings. So the temperature of the ice is reduced because you're just taking heat out of it in order to melt the ice. And it will keep on melting until it reaches the melting point of the liquid above it, so the saltwater mix. So we can use this as a way of measuring how good something is at de-icing things, as to how low a temperature it will get ice to by putting it on, when you put it on the ice.
Right, so when you're gritting the road, what it means is that the temperature outside has to be that much colder in order for the ice or water to freeze.
That's right. So this salt would work down to minus 13 degrees centigrade perfectly fine, but anything below that, it would still freeze.
It's still amazing to think that in order to melt something, paradoxically, you're making it colder.
That's right. But yeah, the energy's got to come from somewhere.
No such thing as a free lunch. Well, what are you going to do next?
Okay, so I've now got 2 more bowls full of ice, and I'm going to put some seawater, which I mixed up earlier, into one of them.
Okay. Another tasty cocktail, courtesy of Dave.
So this has got a few turds, a couple of condoms, that kind of thing, is it?
It
Genuine
was
seawater. Yeah.
No, it was fresh water I mixed with salt, because it's quite a long way to the sea from Cambridge. And just for a change, I thought we'd try some screen wash, which is supposed to be an antifreeze as well. So we'll try putting that one into another bowl.
My screen wash didn't work this winter. Driving down the motorway, completely locked up solid.
Actually, I know several people that's happened to.
Yeah,
they just sort of press the screen wash button and nothing comes out.
Yeah, the whole of my screen wash system froze. You had to hairdry it for about half an hour before I went somewhere just before Christmas.
That's no good.
You should stop washing your hair in your screen wash.
Okay, so now we'll have a look at the seawater and see what temperature it's getting down to.
Okay, using your very high-tech temperature measuring device.
Yeah, this is a radiation thermometer. It can measure temperature things without touching it.
So this is just basically repeating the sprinkling on the salt, but seawater instead.
That's right. We've cooled down the seawater to about 0 degrees C in order to get a fair test. And that comes out at about minus half a degree C.
Oh, so it's not quite the minus 13 then, is it?
No, basically the less salt you have in the solution, the higher the melting point. So seawater isn't actually a very concentrated solution, so it doesn't work very well. Actually, if you had pure seawater, its melting point is about minus 2 degrees C. And actually, I've managed to freeze some seawater with in another
ice,
pot, which is actually just frozen in there.
Wow, you have actually frozen seawater. It's just like being in the Baltic.
So, yeah, I just had another pot of seawater in the ice, in the pot with ice and salt in it, and it's frozen.
Because it's minus 13, of course.
Because it's minus 13.
So the bottom line for Chris Ogilvy's question is that we could use seawater, assuming that the road temperature was not going to drop below 2 degrees, which is the freezing point of seawater. Anything below that and seawater is useless, plus there's the logistical argument you made, which is that you've got to cart 30 times as much equivalent around to get the same effect as the equivalent amount of grit and salt.
That's right. Anything below minus 2 and it will start freezing and you've just created yourself an ice rink.
What about the screen wash and the antifreeze?
Well, the screen wash, which ought to be acting as antifreeze, is working better than the seawater, but not hugely better. It's down to minus 4 or 5 degrees C, so better but not perfect.
Is that 100% concentration?
That was 100% concentration, although it is being diluted as the ice melts, so it's probably a fairly fair test.
And just to follow up on a couple of questions, I mean, how does that actually protect your car? If you put that antifreeze mixture in your radiator, why is that good?
Antifreeze is probably even stronger than the screen wash because it can actually be really quite nasty stuff. It's actually quite poisonous. Basically, it does exactly the same thing as the salt does. It stops the water freezing in the pipes. When water freezes, it expands and can break all sorts of bits of your car apart. The forces it can exert are immense. So it just stops the coolant system in your car freezing, so your car doesn't break apart in cold.
Outstan Jing says on Twitter, at Naked Scientists, if you want to send us a Twitter message, does beer have a lower freezing temperature than water?
Yes, beer's got lots of things dissolved in it. It's got alcohol in there, it's got sugar in there, and basically anything dissolved in water will reduce its freezing point. So beer does freeze at below 0, maybe minus 1, minus 2.
And the CO2, I suppose, if it's fizzy, that will have an effect too.
That will also have an effect, yeah, definitely.
And so if you were to take some beer and put that in the freezer, could you make it much stronger? Is this a way that you could illicitly do a bit of distillation because you'd freeze the water into ice first and then some slightly more alcoholic liquid would be left?
That's right. When you freeze water, it can't take in all these solutes, all these dissolved things into its structure, because ice remains really quite pure. And so what's left gets stronger and stronger and stronger. I don't know if you've ever drunk frozen squash or frozen fruit juice. The stuff which you drink first is incredibly strong, incredibly sugary. And then slowly as it melts, it gets weaker and weaker and weaker until what's left at the end is basically pure water.
Actually, I did used to know someone who was a big fan of beer lollies. Maybe that's why.
Vodka jelly, probably, as well.
Yes.
Thank you very much, Dave Answer, with this week's Kitchen Science. You can find details on the web, presumably.
Yep, at www.thenakedscientist.com/kitchen science.
Some wonderful pictures and Dave's write-up if you'd like to try the experiment for yourself at home, and then you can tell us what you find. Now, Diana, this one for you. You've got the medieval smelly question, now you've got another smelly question. Sandra, I presume that's her name because it's quite a long name she's written here. She says she's in Surprise in Arizona and she wants to know what volume of gas a person has to have, in other words, internal gas, farts, to affect their own weight. Does having gas make you weigh more or less?
Well, we had a bit of a discussion about this, and I think what it comes down to is what your farts are composed of. Of course, there's some hydrogen sulfide in there, and occasionally some methane. I think it depends what kind of bacteria you have in your gut, but I think it was about 5 out of 7 people will have methane produced in their farts. And, of course, methane is lighter than general gas, and therefore you'd think if you had that in your gut, then it would make you a bit lighter. But of course, there's the question of pressure. So if you have a lot of gas in your body that's under pressure, maybe it would actually be denser than air and actually make you heavier. What do you think, Dave?
Yeah, there are various things which could be in the gas. One which could be a really major constituent is hydrogen, which is one of the lightest gases we know of, and that can be up to 50% of your flatulence. And if it's made up of mostly hydrogen, then it's going to be much less dense, and the pressure changes are going to be very, very small. So it could, when you expel the gas, it could even make you heavier because the hydrogen could have been acting a bit like a helium balloon and floating you ever so slightly.
I don't know if you could do a test by seeing if it gives a squeaky pop with a lighted splint.
Maybe a kitchen science for the future.
Yeah.
Got a question here. Never and also Erin asked the same thing. They said, does this whole business of tapping a tin when you've had, say, a drink can come out of a drink dispenser, does tapping the tin to stop it exploding all over you really work, or is that a myth?
It does certainly have an effect. The theory is, or it can have an effect. Haven't got it to work 100%, but it's supposed to help. The idea is that if you've shaken up a can, the reason why it explodes is there's lots of little bubbles in there already of carbon dioxide in the in the liquid already. That gives the gas lots of places to start bubbles, and they can get bigger very, very quickly, so it all explodes and forms a foam. If you tap it, the idea is you dislodge the ones which are stuck around the bottom and on the sides. So you've got fewer bubbles in there at the bottom, so it makes a foam much more slowly and it doesn't make a mess.
Terrific. Thank you, Dave. I'm just going to sneak this one in, which is E. Hill Burns on Twitter, at Naked Scientist, wrote to us, said, do all satellites go around a planet? And he also then says stars and other things, so I think we're presuming non-man-made satellites in the same direction. And if so, why? Well, the answer is effectively yes, because they condense out of what's called a protoplanetary disk, which is a big spinning disk of material which initially starts off as an envelope around the star which is at the centre of the solar system, or the particular galaxy area you're talking about. And that then condenses into planetesimals, little objects that become and accrete into the big objects. And conservation of angular momentum means they're all turning, and once you've done all the equations and everything has collided with everything else it's going to, you end up with something that usually is all turning in one net direction. That's not to say that big collisions can't come in and then turn things around a bit, and we think that Uranus is turning on its side because it is, possibly because there was a big collision with something else way back in history, and that's what made things actually turn around in that rather strange way. So the answer is yes, we think things do go around in one consistent degree, a direction in the same plane, but there are exceptions at the level of individual bodies which can spin in funny directions. Right, now it's time for this week's question of the week. Diana?
Well, this week it's all about how to look good with a gecko.
My name is Luke McNeil, and my question is, it's often said that people resemble their pets or vice versa. Is this a phenomena that has been studied? Do people choose pets that resemble them, or is this a matter of us noticing when people do resemble their pets and forgetting when we see people who do not resemble their pets?
So, is it a matter of selective memory or selective image?
I'm Dr. Lance Workman. I'm a psychologist at Bath Spa University. Well, I think there are two reasons why pets look like their owners? The first reason is that we tend to buy pets, and dogs in particular, that fit in with our lifestyle. So if you're an active, robust person with lots of energy who likes to be outdoors a lot, then you may well buy a dog that is likewise full of energy. It's a bit like selecting a spouse. It'll work really well if you find someone who fits in with your lifestyle. That's the first reason. I think the second reason is a more subtle one, and that is that I think we're drawn to others that look a bit like ourselves. It's a bit of an old Freudian notion, but I think it does stand up to scrutiny. So at some sort of subconscious level, when we choose a pet, we're looking for something that in some way reflects ourselves. I think there's both of these reasons going on there. I think you begin to look for similarities rather than differences. So I think if we say, oh, here's Fred and here's Jack Russell, don't they look similar? You're already led along that path. There's something that some people call the confirmation bias. So, for example, if you go to a fortune teller and they say 6 things out of 20 that are correct, you go away and you remember those 6 things and you forget the other 14. And my own study suggests that people get this right about 2/3 of the time, maybe 60%, something like that. So there's a good 30 to 40% of the time they get wrong in matching pets up to their owners. So I think we remember the ones we get right. But again, 2/3 is well above chance. So it's a mixture of some real truth in the idea that we look like our pets and the fact that we look for evidence that supports that case.
Diana, owner of 2 Rottweilers, and I'm just joking.
Oh, shut up. I know you own a weasel, don't you, Chris? Yeah, meow. So although we do tend to remember better those pets which resembled their owners, it looks like many pet buyers will tend to choose animals which look a little bit like they do. And in Lance's research, he tested this by showing 70 volunteers photos of dogs and dog owners and asked them to match one to the other. And 60% of the time, they got it right. I wonder if the same is true for cats, because they tend to be a bit more sort of homogenous in terms of shape, I think, possibly. Well, next week we'll be researching another sort of pet.
Hi, naked scientists. I'm Jan from Norwich, and I'm the captain of a large oil tanker. I have a question about pigeons. We often get flocks of wild and racing pigeons land on our decks, and they can stay for weeks until the crew have fattened them up for the pot, that is. My question is this. Does the steel in the structure of the ship, which is about 50,000 tons, affect the pigeon's navigation system? I have heard that they rely in part on the Earth's magnetic field.
Can migratory birds be pulled off course by large steel objects like Jan's 50,000 tonnes of steel tanker? Let us know what you think by email. It's chris@thenakedscientist.com, or write your answer on the forum for us to read out. And the forum is at thenakedscientist.com/forum.
And if you have any fancy pigeon-related recipes for Jan to take with him on his next set of travels, then you can send those in too. And interestingly, Diana, I've just seen pop up here, Amateur Scientist has just written into our Second Life site, but many pets are also given as gifts. So presumably, if what you're saying is true, then the person giving the gift must also think that the gift looks a bit like the presumptive new owner. Would you agree?
I think that's a bit presumptive of the gift giver, isn't it?
You can get your words together better than I can this evening. Thank you very much, Diana O'Carroll, with this week's Question of the Week. And you can get that again through our website as its own independent podcast on iTunes or at nakedscientist.com/QOTW. Well, that's it for this week. We have run out of time. Thank you for all your questions, thoughts and comments. Keep them coming in, do. It's chris@thenakedscientist.com, or follow us on Twitter @nakedscientists. Next week, we're back with a look at what happens when you blow things up. We've got an explosive bit of broadcasting for you, looking at the science of landmines and how we study them safely, and how we build better vehicles that are more landmine resistant. We'll also be looking at how you study explosions safely in the laboratory and what happens when you blow stuff up underwater. If you've got any explosively oriented type questions, then do send them in. It's chris@thenakedscientist.com. Thank you to our wonderful production team, Ben Valsler and Mira Senthalingam, and our other 2 wonderful team members, Dave Ansell and Diana O'Carroll. Until next time, goodbye.
The Naked Scientist podcast comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC and UK FAST. For more information, look us up online at nakedscientist.com.